Hi, Assalamualaikum Dr. Shamila. My name is Muhammad Yasir bin Muhammad Yurid. My metric number is 301-747. So today I'm going to talk about topic differential and integral calculus of functions of several variables. So let's start with a concept of differential and integral calculus of functions of several variables. Differential and integral calculus of functions of several variables is an advanced branch of mathematics that deals with the study of functions that depend on multiple independent variables. Unlike single variable calculus, where functions depend on only one variable, functions of several variables introduce a more complex and multidimensional aspect to the analysis. Differential and integral calculus of functions of several variables is important in mathematics. This is because it is capable to modeling complex system, optimizations problem, application in engineering and physics, scientific research, vector calculus and physics, partial differential equations, machine learning and data science, and numerical analysis. Differential and integral calculus of functions of several variables have been applied in our life in various fields such as game development, astronomy and astrophysics, physics and engineering, economics and finance, chemistry and chemical engineering, environmental science, statistics and data analysis, biology and medicine, computer graphics and animation, robotics and autonomous system, and optimizations problem. Now, let's see the overview of differential and integral calculus of functions of several variables. It is composed of functions of several variables, partial derivative, multiple integrals, gradient, and chain rule. Functions of several variables depend on multiple independent variables, typically denoted as S1, S2 until S1. A general function can be represented as f S1, S2 until Sn. For partial derivatives, it is measure how a function changes concerning a specific variable while holding all other variables constant. The partial derivative of f with respect to s is denoted as delta f, delta si, or fsi. For multiple integrals, it is calculate accumulated effects of functions over regions in multiple dimensions. The n-dimensional integral over a region R is denoted as triple R f s1, s2 until sn, delta s1, delta s2 until delta sn. For gradient, the gradient of a function f s1, s2 until sn is a vector that points in the direction of the steepest increase of the function at a given point. It is represented as delta f equal to delta f, delta s1, delta f, delta s2 until delta f, delta sn. For chain rule, it is help us to find derivative of composition of functions. The chain rule states how changes in one variable affect the changes in another variable through an intermediate variables. A lot of theories and law used in this topic. The number one is partial derivative theorem. If a function f has continuous partial derivative with respect to all its variables in an open region, then the order of differentiation does not affect the result. Number two, Lagrange multipliers. The problem can be formulated as solving a system of equations involving partial derivative and the constraint. Number three, gradient theorem. Line integral of the gradient of f over a curve C equal difference in the value of f at the endpoint of the curve. Number four, Green's theorem. Relates a double integral over a region in the plane to a line integral around the boundary of that region. Number five, divergence theorem. Gauss theorem. Relates a triple integral over a region in space to a surface integral over the closed surface enclosing that region. Number 6. Stokes theorem. Relates a surface integral of the curl of a vector field over a surface to a line integral of the vector field around the boundary of the surface. For next slides, I will pass to my partner.
Assalamualaikum warahmatullahi wabarakatuh. I'm 2988484 Muhammad Matiki Basri, and today I'm going to explain about how to solve this equation. Okay, first, suppose we have a three-variable function that represent the temperature distribution in a three-dimensional object. T, x, y, and z equal to x power of 2 plus 2xy plus 3yz, where t is the temperature and x, y, and z represent the spatial coordinate. To find the mixed partial derivative, t with respect to x and y, and t with respect to y and z using the partial derivative theorem, according to the theorem, this mixed partial derivative should be equal. Okay, first we're calculating the partial derivative of t with respect to x and y. To find the partial derivative of t with respect to z and y, we first take the partial derivative of t with respect to x and then with respect to y. Okay, you can see how this calculate. Now we take the partial derivative of t with respect to x with respect to y. Okay, the second one, we need to calculating the partial derivative of t with respect to y and x. To find the partial derivative of t with respect to y and z, we first take the partial derivative of t with respect to y, and then with respect to x. Now, we take the partial derivative of t with respect to y with respect to x. Since both partial derivative of t with respect to x and y and partial derivative of t with respect to y and x are equal to 2, this result is consistent with the theorem statement. Okay, find the dimension of the box with largest volume if the total surface area 64 cm2. We want to find the largest volume, and so the function that we want to optimize is given by f bracket x, y, z equal to x, y, z. Okay, we need to maximize v subject to constraint s equal to k, where k is the constant fixed surface area. Since the total surface area equal to 64, 2xy plus 2xz plus 2yz equal to 64, and turn out them into xy plus xz plus yz equal to 32. Let's gx equal to xy plus xz plus yz. Okay, first, yz equal to lambda bracket y plus z, fx equal to lambda gx. The second one, xz equal to lambda bracket x plus z, fy equal to lambda gy. The third one, xy equal to lambda bracket x plus y, fz equal to lambda gz. And the fourth one, xy plus xz plus yz equal to 32. Bracket g bracket x y z equal to 32. Okay, multiply x, y, z into the equation respectively to make the left hand side to be x, y, z. Okay, fifth, x, y, z equal to lambda x bracket y plus z. The sixth one, x, y, z equal to lambda y x plus z. And the seventh one, x, y, z equal to lambda z bracket x plus y. Set equation 5 and 6 equal lambda x bracket y plus z equal to lambda y bracket x plus z, lambda bracket xy plus xz minus lambda bracket xy plus yz equal to 0, lambda bracket xz minus yz equal to 0, and then lambda is equal to 0 or xz equal to yz. Since yz is equal to 0, we will get two possibilities, which is yz is equal to 0, y equal to 0, or z equal to 0. Since we are talking about the dimension of a box, we can discount lambda equal to 0 and get xz equal to yz. Since we know that z is not equal to 0 because the dimension of a box, we can cancel the z from both sides. This gives x equal to y. Now let's set equation 6 and 7 equal lambda y bracket x plus z equal to lambda z bracket x plus y, lambda bracket yx plus yz minus zx minus xy is equal to 0, lambda bracket yx minus zx is equal to 0, and then we're gonna get lambda is equal to 0 or yx is equal to zx. Since we know that lambda is equal to 0 won't work, and so this leaves yx is equal to zx, we can also say that x is not equal to 0. Since we are dealing with the dimension of a box, so we must have z equal to y. Plugging equation x and 9 into equation 4, we get y power of 2 plus y power of 2 plus y power of 2 is equal to 3y power of 2 is equal to 32. So, however, we know that y must be positive since we are talking about the dimension of a box. Therefore, the only solution that makes physical sense here is x equal to y equal to z, and z equal to 3.266. Let's choose x equal to y equal to 1. Plugging this into the constraint give 1 plus z equal to 32. 2z equal to 31, and then we're gonna get z equal to 31 over 2. So this is a set of dimension that satisfy the constraint and the volume. For this set of dimension is v equal to f bracket 1 31 over 2 equal to 31 over 2 equal to 15.5. Let's compare to 34.8376. The new dimension gives a smaller volume, and so our solution above is, so the dimension that will give a maximum volume of the box are x equal to y equal to z equal to 3.266. In conclusion, differential and integral calculus of function of several variables play very important role in understanding and analyzing complex phenomena in various fields, including mathematics, physics, engineering, economics, and so on. This branch of calculus extends the concept of differential and integration from single variable function to multivariable function, allowing us to study how multiple variables interact and affect each other. Integral calculus of function of several variables allow us to calculate volume, area, and surface integral in multi-dimensional domain, which is crucial in solving problems related to mass distribution, probability, and flow analysis. It also provides a powerful tool for solving partial differential equations that arise in various physical and engineering applications. The study of differential and integral calculus of function of several variables need further exploration and study to tackle a real-world problem that cannot be adequately addressed using a single variable calculus. By mastering this subject, we gain a deeper understanding of how interconnectedness of variables influence the behavior of complex systems, paving the way for advancement in science, technology, and decision-making process. Okay, that's all from me. Thank you.